All right. Welcome, everybody. Looks like we've got some people in here. Hopefully, get a few more people coming in. Um, so, welcome on in. It's been, a week or so since we've met for class. So, a couple of things here. We're just going to go over some new material. So, make sure you're taking your test. Make sure you're getting that taken care of. I sent out an announcement a few minutes ago that I just want to make sure everyone's aware of. Remember, I talked at the beginning of the semester about um, having to do drops. We have to clean up the roster, basically. So next week, I will be dropping students who are not making sufficient progress in the class. So the three things I'm going to be looking at, and I'm not trying to make anyone feel bad or anything. It's just that's one of the things we have to do as a professor is make sure students are progressing. And when students aren't, we're supposed to clean up the roles a bit. So three things that I'll be looking at early next week are: did you take the exam that you were supposed to take? Right? If you didn't take that exam, there's not much chance of you passing the class. How much homework has been completed? So are you roughly where you should be as far as homework? Now, I get it. Sometimes people are behind a section or two, or maybe there's a couple problems along the way that you didn't get. I don't expect you to have 100% in homework at this point. But can the case be made that you're making realistic progress towards finishing a class? At the beginning of next week, we'll be halfway through. If you are an entire chapter behind, or you're a chapter and a half behind, it's not very realistic that you're going to catch up and be successful for the rest of the course, right? So how much homework has been completed? Again, if you're like one section behind, you don't need to email me about that. Or if you've done most of it, but there were a couple problems here and there you didn't get, that's one thing. Basically look at it and ask yourself, does this look like someone who's roughly up to date and putting in the hard work of trying to complete this course? If you're a chapter behind, then in all likelihood you didn't do well on the exam, and then also you're behind in the homework. So that's not good, right? And then also, is the student regularly attending class meetings? So remember, I take roll. The catalog says after a certain fraction, it's small, it's like 1/9. So for us, that's like 2 absences. I won't drop people just for having 2 absences, but once you start having 3, 4 absences and you also are behind on the homework, then there starts to be a case that you're not really progressing in the course. So it is not a part of the job that I love. I'm not really a big fan of dropping students, but it's one of the things we have to do, especially in this new era of online classes, where some people do not progress. We have to sort of make sure people are progressing, and people who aren't progressing, we clean it up. So I'm telling you that now because it's Thursday. The very earliest I would do these drops is Monday, and it might even be Tuesday. I don't know, Monday or Tuesday, I'll take a look at doing that. So the point is, if you are behind in your homework, take the weekend to get yourself caught up. Then when I look at it on Monday, instead of being a chapter behind, maybe you're 2 sections behind. That might be the difference between you getting dropped and not getting dropped. So I'm giving you a heads up so you have time to work on it, so that when I look in there, I go, oh, no, this person, yeah, they're behind. Who knows if they'll pass or not? But at least they're still participating. At least they're still trying to progress in the course. When I look and I see people where the work has fallen off, they're very far behind, that's this kind of stuff that's going to get cut loose. So again, I know it sounds like a big negative. I'm actually telling you as a positive so that you can, if you're a little more behind than you should be, take the next few days to get yourself caught up. Okay? Like now's the time. This is kind of a pivotal point. We're at halfway. If you're significantly behind at halfway, your chances of finishing strong are not good. If you're a little behind, 1 section, 2 sections, sure, person can, throw an extra day at it and get themselves caught up or whatever. Okay? So, so enough of that sort of unpleasantness. So some of you have taken the exam. Some of you will be taking the exam today or tomorrow. Some people are taking the exam at this very moment. So it just sort of depends on what you were able to get worked out. Tomorrow, I will be getting the exams from the testing center, and then I will be working on grading them. So, but because because you have until late Friday to do the test, that means I'm going to pick up the tests, but they probably won't really get taken care of until like Monday. So what will happen is Monday or Tuesday of next week, probably Monday, I will, inside of the XYZ homework, I'll add a column inside the grade book. So if you look in the grade book in XYZ homework, it shows you all the grades for your homework. You will also see the exam. I'll put the exam scores in there so that you can see what that exam grade looks like. Keep in mind the total grade inside of, like, in the XYZ homework, that doesn't account for any kind of Canvas stuff or anything like that. So it's not your total point grade. Just look at individual scores. So in other words, there's going to be a column that gives you your test score, and then you'll have the columns that have all your tests, your homework scores and stuff like that, right? It doesn't mean your score for the whole class. That can be figured out pretty easily because you've got your test score, you've got your homework score, and then whatever the participation score, and you just multiply those by the weights, and then you've got your class grade, right? But the key is you'll be able to see your test grade probably Monday, maybe Tuesday, and then you'll know how you did, okay? So make sure you get that taken care of. Oh, and I will, let's see, is this like the other class? Nope, we've got everything open, so we're all good to go. Okay, so that's good. And then, so before we move ahead, is there any questions on anything? Does anyone have questions about like this point in the class or like whatever, how things are getting done? Everyone's clear on everything up to this point? Okay, great. Feel free to ask if you have a question. Go ahead, throw it into chat. Take care of that. One thing that I noticed today, apparently I've been putting the wrong date on the streams when they get cataloged on YouTube. For some reason, I was putting 7 for June when July is 7 as far as month numbers go. So apparently I messed that up, but I think by looking at it, you'll figure out what the dates are. So, right. So, all right. So with that said, we're going to move ahead. We're going to finish up chapter 3 that we're looking at. And I'm not going to spend a ton of time on it because it's kind of just, like with optimization, you're pretty much going to look in the book and follow along the examples. There's just a few different types of optimization. Follow the example in the book. Watch the video that has to do with the homework. It's not really anything new mathematically. You're basically using the first derivative test and the second derivative test in order to make statements and optimize things. Because you are, when you optimize, you're generally trying to find a maximum or a minimum, right? It makes sense. We would want to do things like maximize profit, and we might want to do things like minimize cost, right? That seems reasonable. So optimization does that. It helps you find on your graph the exact point where that maximum is occurring or that exact point where the minimum is occurring, and then you can make informed decisions for your business. In this case, is business calc. It's usually business applications in here, but whatever it is that you're trying to do. And remember, we're doing this algebraically. We're using the tools of calculus because it can give us those points exactly, right? If you're running a business, do you want to be kind of in the neighborhood of maximizing your profit, or do you want to know exactly how to maximize your profit, right? That's why we don't just plot these things, look at a graph and go, oh, well, that kind of looks like maybe that's about the maximum. We want to use the calculus to be able to say, you want to sell exactly this many units in order to maximize profit, right? Because stuff's competitive. You want to be able to make the most amount of money that you can for certain stuff. So we'll look at optimization a little bit. I'll explain elasticity a little bit. So I'll go over that and explain what we're talking about. And then we're going to go ahead and move into chapter 4, right? So I'll give you enough information that I feel like you can kind of make sense of the optimization and the elasticity. There are some videos in here. So we've got this video and then the elasticity video. And then I'll talk about it here in class. Oops, now I'm not, get back here. So you should be able to get through those. And then we'll go into chapter 4. Let's see. So there's a couple questions here, it looks like. So let's see. I forget off the top of my head. So there's a question in the chat about homework. Basically, you always want to look at the calendar and XYZ homework. So basically what I'm doing here, oh, my window is way too big here. Let's move that. So when you're trying to figure out when stuff is due, you'll just go to the calendar here. And let's go ahead and make it the 6-week calendar. So, oh, it doesn't do what I thought it would do. Okay, so question is about chapter 3. So chapter 3 is due tomorrow, right? The 7th? Yeah, so chapter 3 is due tomorrow. So the 2 sections you should already know how to do. The other 2 sections we're discussing today. And if you just kind of follow along the videos that are in the homework, you should be good to go. Okay, is that the question? And then hopefully by the middle of next week, you should be able to do chapter 4, since we're going to start talking about chapter 4 and then go from there. Sometimes, so I haven't heard about multiple, so there's a comment in the chat. Multiple students and I have had issues with XYZ rejecting correct answers. Is there any way to resolve that? So the way you would want to resolve that is send me a screenshot of it happening, because that's a thing I haven't really heard about. And sometimes when we use these different homework platforms, students will say, oh, I put in the right answer, but it was giving me the wrong answer. And sometimes the student is wrong. And sometimes it's not the student who's wrong, it's poor programming. Like this is one of the reasons I switched away from Pearson. Pearson was terrible about this. You know, it will show you at the end of a problem on Pearson, it would say like, the correct answer, it would say like you're wrong, and then it would say the correct answer is x equals 3, and then your answer x equals 3, and they look identical. But like on Pearson, a popular thing is if someone accidentally hits the space bar and it puts a space in there, it'll mark it wrong. So sometimes it's actually the student who is wrong, and sometimes it's not, but it's almost impossible for me, just from students saying that it gave them a wrong answer, it's impossible for me to know. So if there are issues with XYZ homework, what you want to do is at the time that it gives you, that like you can see that it's marking you wrong when you're actually correct, what you want to do is take a screenshot and send that to me. So if there's a screenshot, then I can look at it and go, oh, yes, you actually, you know, it happens both ways. Students send me a screenshot and I go, oh, that's actually not the right way to do it. Or sometimes a student will say like, you know, like they don't really like it when we have negative exponents in an answer. So a student's answer might be mathematically correct, but they're still using negative exponents or something. So then, you know, it might be mathematically correct, but it's not the way you're supposed to answer the question. So sometimes that happens, and sometimes it's just wrong, right? So screenshots are basically the way to do that. Yeah, so feel free to email me if you have concerns about it. Send me give me enough information that I can follow. Like, make sure you understand I'm not in the room with you, like looking at it. I have to sort of be a detective and figure out everything after the fact. So make sure that your screenshots and stuff like that really show me what's happening, right? Because sometimes I've had students give me a screenshot that's so small, I can't even figure out like what problem they're working on or anything like that. Like if they take the picture with their phone, all I see is like the box that they've got a number in, and I don't even know what problem it is. So please just try to keep that in mind. Like, understand I have to figure out everything from your documentation. So explain to me what problem, what homework section, show me the screenshot of it marking you wrong. Like, don't just tell me it marked you wrong. Like, show me that screenshot so that I can see exactly what it's telling you is wrong or whatever, okay? Sure, let's see. So there's a question about a certain problem. I think, yeah, we should have time to go over stuff today. So let's see. Question 10 or 11 from 3.1. Okay, let's double check those. Let's see. So let's go here. Give me 1 second. Yeah, so hopefully that answers everyone's question about those things. Okay, 3.1. 3.1, 10, or 11. Let's take a look. As far as will the exams be curved, it's unlikely they'll be curved, but I haven't even seen the exams yet, so I have no way of knowing. I don't have any information as far as what's happened with the exams yet because I have not picked them up. Let's see. So one of these says use Wolfram Alpha. Oh, so like 11 and 12, I think is what David's talking about. Use the one with Wolfram Alpha. So let me double check here. I don't usually use Wolfram Alpha to do them, so let me remember exactly what it is they're wanting you to do. Sometimes off the top of your head, when you see a problem, you kind of haven't done it for a while, so you forget exactly how they want you to do that. I mean, at the end of the day, you're ultimately just using your first and second derivative test. So I have to remember exactly how they want that done for using Wolfram Alpha. Let's see. Let's do it this way. Try something. Give me 1 second here. All right, let's take a look here. Let me find a piece of scratch paper. Okay, let's take a look at this problem. So we've got so the problem where it shows me, everyone's should be a little bit randomized, but the one it's showing me for this question is 1/4 x to the 4th plus 5/3 x cubed minus 9/2 x squared minus 45x. Let me double check I've got that right. Hate to do a whole problem and then it doesn't come out right. Okay, so let's see. Let's fire up Desmos and take a look at that. So we've got 1/4 x to the 4th plus 5/3. Oops. How did it do that? 1/4 x to the 4th plus 5/3 x cubed minus 9/2 x squared minus 45x. Is this right? 1/4 x to the 4th plus 5. thirds x cubed minus 9 halves x squared minus 45x. Okay, and then we can play around with this window here. Let me move this so it fits a little better, and we'll move this over to there. See if we can make a better window. So if you click this wrench, you can change the settings. Just a quick overview on Wolfram operation would be good. Okay, so yeah, so I don't actually use Wolfram Alpha very much, but we'll take a look at it. As, again, I'm not sure exactly which part they want you to do there. So I'll have to remind myself. So you can go in, you can make it bold by clicking this, and then you can change your axis so we can actually see the things. So say we want to go from negative, I don't know, let's get a good idea where this thing exists. Nope, looks like we don't need that. So -5. And then, okay, so you don't need the whole question gone over, because I think that's kind of an in-depth question, but just a quick overview on Wolfram Alpha. So I can show you Wolfram Alpha a little bit. I do keep it open as a tab, but I don't usually use it for these kinds of problems. So Wolfram Alpha is basically a, they call themselves a computational engine, right? Now they talk about computational intelligence, and that's all sort of changing now that, you know, in the last 6 months that AI has become a whole new thing. I think Wolfram Alpha is sort of going to have to adjust with that. But the way that Google is a search engine, right? Google doesn't actually figure anything out or calculate anything. They just go find on the web for you where stuff is. And if you put into Google something like weather in Ventura, it'll tell you the weather, but Google didn't calculate that. They just went to the Weather Channel and like stole that data and then told you what the weather was, right? So Wolfram Alpha is a computation engine. They basically want to be the fanciest calculator out there, right? They want to be able to do all that kind of stuff for you. So you can do a lot of things on Wolfram Alpha, and you might find it frustrating that certain things on Wolfram Alpha are like, well, why did I have to learn to do that by hand if I can do this on Wolfram Alpha? And the answer is because you have to understand what you're doing, right? You never want to be using a computational tool where you don't actually understand what's happening. When people do that, when you give someone a tool that they don't understand, bad things happen, right? You do that in a woodshop class, you give someone a tool they don't understand how it works, they're probably going to hurt themselves, right? You do it in a setting, a financial setting, where you give someone a tool, they don't know how to use it, but they use it anyways, probably someone's going to lose a lot of money, right? So you always want to understand a tool when you use it. So Wolfram Alpha, like, we make you learn this stuff, but then, you know, a lot of times in real life, if we have a complicated equation to solve, you go have Wolfram Alpha figure it out for you. So you can put in things like, say, solve. And again, you use the caret, the shift 6 button, if you want to use an exponent. So I could do like 21x squared minus 13x plus 7 equals 0. So I just made up that polynomial. I'm telling it to solve it for me. I hit equals, and Wolfram Alpha is going to go through and say, did you mean 21x squared minus 13x plus 7 equals 0? And I'll say yes. And then it says, well, here's your answer, right? So it solved that equation for me, and it gives you some additional stuff that you don't necessarily, sometimes is helpful, sometimes not. They throw some stuff at you, but you got your solutions, right? So that's largely where Wolfram Alpha is helpful. Now, there are other things that Wolfram Alpha can do for you. For example, if you go into examples here, you'll have things like they have different math topics, right? You're in a calculus class, so you could click calculus, and you could see what topics Wolfram Alpha can do for you. So you'll see right here, in a week or so, I don't know, about a week, I guess, we'll be in the integral calculus, so you can see it's doing integrals for you. Over here, we've been learning about derivatives, and you can see it does derivatives for you over here. So you can have Wolfram Alpha do integrals and derivatives for you. Now, I would be careful because sometimes Wolfram Alpha gives their final solution in a way that is not very simplified. So this may be one of those cases where, like, if you just, this is sort of unethical, you won't really learn what you're doing. But if you use Wolfram Alpha to get your homework answers for you, it's entirely possible that the form you put them into the XYZ homework, it's going to go, nah, I don't like this answer. It's not good. It's going to mark it wrong. And you're going to go, well, it is wrong. I mean, it is right because Wolfram Alpha told me so, but it has to do, again, with putting it in the right form, right? Understanding your answer enough to put it in the correct form and make that interpretation. So you want to kind of, go from there. So you can have it calculate a derivative for you, but again, I wouldn't use Wolfram Alpha to like do your homework for you. You use it as a calculator to help you along the way. You want to understand what's actually taking place when you do things. So you could go into Wolfram Alpha and have it say, for instance, we're back here. We could say take the derivative of that polynomial, and it says, oh, did you mean the derivative with respect to x? So this notation should look familiar. Let me make this a little bigger. The derivative of 21x squared minus 13x plus 7, it's going to go, oh, that derivative is 42x minus 13, which hopefully everyone watching knows, oh, yeah, that's right. That's how you take the derivative of a polynomial. So it's giving you that answer. So the key for these, for Wolfram Alpha using stuff, is really to go click examples, go down to the class you're in, which in this case is calculus and analysis, and it's going to give you a list of things it could do. Here's some limits that it can calculate, right? It can help you with limits. Let's see. In this class, we don't really do sequences or sums, so it's not going to do that. But there's we will do area between curves later, and this can help you with that. But again, like, what's probably going to happen when we do areas of curves in the book, we'll calculate exact areas between curves. And here on Wolfram Alpha, it's usually going to give you a decimal approximation. So if you take the answer from Wolfram Alpha and try to put it in XYZ homework, it's going to go, that's not the exact answer. You might have a couple problems like this where they say go use Wolfram Alpha, but you're not going to need it you won't. For most of the problems, you're probably not going to want to just plug the answer in here and get the answer, or plug the problem in here and get the answer, partially because you're not learning it, but then also because the answers aren't going to line up perfectly. Okay. So that's kind of the overview. So as far as this problem that it was asked about, 11 and 12, it's essentially, so for the first one, they want the relative max and min. So it's just first and second derivative, except you can use Wolfram Alpha to get, it's telling you use Wolfram Alpha to get those derivatives for you. Like, let's see, we might be able to just, what if we take that one? I wonder if we just do maximum of, let's see, 0.25 x to the fourth plus 5/3 x cubed minus 9/2 x squared minus 45x. In fact, I'm going to, looks like I have a typo here. Let's just change that to be 1/4. So notice how I'm putting these in here. I'm putting the parentheses and then I'm putting the fraction inside of it. It's because you have to be very careful. Notice when you have it calculate something on Wolfram Alpha, and I'm not even sure if this is the right command for this, but notice how it formats it for you. You should always check that that formatting is correct, because it's possible, like say I do this, say I don't put those parentheses in there, I bet it's going to do this one wrong. Nope, it still got it right. But sometimes it'll do things like take this x cubed and put it in the bottom of the fraction, because it's confused by the way that you're entering the numbers in there. But in this case, when we look at it, we go, nope, that's the right one. That's correct. So what it's, yeah, so it read it correctly. So double check that. And then it's coming down and saying the max. And then make sure your answer makes sense. Don't just blindly take something from Wolfram Alpha and put it into the XYZ homework. But we're looking for a maximum, which would be a relative maximum. And as we can see from our graph here, there's only going to be one relative maximum, right around in this area somewhere. We don't know exactly where. But it looks like it's telling us that occurs at x equals -3. Right? So the relative maxima would be occurring at x equals -3, and it looks like it's 279/4, right? So let's see if they like that as the input. Nope, it doesn't. Oh, it wants it in a point form. Okay, so when it wants, for that answer, when you're finding the relative maxima, it wants you to give it as a point. So in other words, -3 comma 279/4. Yeah, okay, gave me, I answered one of the two. So it wants it as a point when you enter it. So the point would be -3 comma 279/4 would be the answer on that part of the problem. So it's just a matter of like finding the right function for what it's trying to have you do in Wolfram Alpha. And sometimes you just try it. Like there's nothing, like if you try something on Wolfram Alpha and it doesn't give you the right thing, you just try something else. You didn't lose anything, right? So sometimes it's kind of a matter of trial and error, or like I say, if you can go into examples and look around to try to get it to find to do certain things for you. So there's a question in chat here about what grade you need to pass the class. So that's all in the syllabus. You need a 70% basically in order to pass the class, but there's also a minimum amount of homework you have to do and stuff like that. So check the syllabus. That should have all the information that you need on passing the class. And if you have specific questions, feel free to ask me after class. Okay, so I think that kind of answers that. Yeah, good question. Good question about the Wolfram Alpha. Okay, so let's dive into a few things here. We'll look at applications of optimization. So I want to go over this strategy a little bit, just a few steps to help. Like every optimization problem is different, right? They're just all a little bit different than each other. So it's not like you can memorize how to do them, but a lot of them fall into the same basic category. So once you've done a few of a certain kind, you kind of know how to adjust it to make it fit into the other ones. And here's a good helpful strategy for doing optimization problems. Okay. So one is draw a figure when one is appropriate. In other words, draw a picture. This can always be helpful. You'll see when they're doing problems, see how they're drawing some pictures here with the areas that they're representing. If you draw a picture, like people try to do this in their head, never a good idea, right? If you're doing something mathematics related, just write it down. You'll work so much faster if you're writing things on paper than if you're trying to do things in your head. It's not a good idea. So draw yourself a picture to represent what's going on. Then you can start labeling variables and all that kind of stuff. Okay. Step 2, assign a variable to each quantity mentioned in the problem. So start trying to see what variables you can use to represent the things that are given in the problem, and then see if sometimes you can reduce the number of variables that you're using. Like you might start off with a box here where you've got your length and your width, like this. But then they tell you at some point, what do they tell you? They'll give you some condition in the problem that sometimes means you can replace one variable. Like what if they say the length is 2 times the width? Well, then you could replace this L with 2W. And every time you reduce the number of variables in the problem, you make that problem significantly easier to do. Sometimes it goes from impossible to possible by reducing that number of variables. So if you did a problem where they said the length is twice the width, you would want to write the length as 2w, because then you only have the one variable that you're dealing with, right? Step 3, select the quantity that is to be optimized and construct a function that relates it in some or all of the other quantities. So like this problem down here that we're looking at, the thing you're optimizing is area, right? Given a certain amount of fencing, given a certain amount of fencing, how do you maximize the area? So maybe a farmer has a certain amount of fence left over. They want to maximize the grazing area, but they want these sheep fenced in so that they're protected or they don't wander off or whatever. So you want the area to be maximized, but with only a certain amount of, fencing or whatever, right? So you create your function that you're going to optimize. This is the example that is probably best seen, or this is the step that is best seen by looking at examples, right? What I'm saying is, many of these problems have slight variations on each other, but like this problem down here that's maximizing area, you're going to take a very similar approach to any area maximization problem that you approach, right? You're going to do this area in a pretty similar way. Okay, so definitely like go to these examples and try to look at them and figure out how they're doing that thing. Step 4, since all the rules of differentiation deal with functions of only one variable, I don't know if I'd agree with that statement since we have implicit differentiation, but the function must involve only one variable. It is in our best interest to write a function of only one variable. That is true. If the function constructed in step 3 involves more than one variable, use the information contained in the problem to eliminate variables until you have found a function of only one variable. So that's the step I was mentioning a minute ago. I kind of talked about it up here in step 2. Because you can do it in step 2. When you're first assigning variables, sometimes it's really convenient to right at that point go, let's eliminate some of these variables. They're telling you to do it down in step 4, whatever. It's just, it doesn't really matter when you do it. As long as you eliminate those variables, then you're good to go. Now, be aware this is not always possible. Some of you have to take semester 2 of this course, which is multivariate functional calculus. And I believe in our district, the only school that currently offers that is Moore Park. So if you need that second semester, you'll have to take it at Moore Park or somewhere else. We don't offer it at Ventura, and I believe Oxnard does not offer it, at least not at this time, so I'm not sure. So just know sometimes you cannot eliminate that variable, but sometimes you can eliminate the variable. Right? So, sorry, okay. So if possible, and for this class, it will be possible for you to eliminate those variables. Just know in the real world, sometimes you can't always eliminate the variables. And then step 5, use differentiation to find the critical values of the function and apply the test for absolute extrema. Disregard all answers that are not relevant to the situation. So what they're saying in step 5 is basically use the first and second derivative tests. That's what they're telling you to do. So the first and second derivative test, you're going to apply it to the derivative, see what it tells you, right? And they say disregard all answers that are not relevant to the situation. So you might be given a function that exists over in the negative x territory, but that function represents number of units sold. Well, does it have any meaning to sell negative 1,000 units? Probably not for the situation that you're looking at, right? So what that means is ignore certain parts of the graph. Also, there may be times when creating too many units actually cuts your profit down and you actually go into negative territory again. Well, you're probably not going to do that where you decide to sell so many units that it actually ends up destroying your profit. So then you can ignore that part of the graph. Just ignore the part of the graph that makes sense, that is reasonable for the problem that you're looking at. That's what they mean by disregard all answers that are not relevant to the situation. If they either completely don't make sense mathematically, or maybe they make sense mathematically, but they make no business sense for you to do that, then obviously you don't go with those answers, right? You basically make smart decisions is is what we're looking at. So then there's some examples in the book. Feel free to, like I say, browse the examples and just try to find the one that's similar to the one that you're working on in a particular problem, right? And then sort of work through it. Also, each problem has the videos, and they have the oftentimes there's the what is it called, where they like work out the solution or whatever. Here's a problem. This is one of the few times we have something that's outside of the business application. Like most of the problems in the book are business applications. But here's one about drug concentration. So this is kind of interesting because you kind of wonder, like, well, how does drug concentration work? When you go to the doctor or if you're at the hospital or something and they put some stuff into you, well, does that mean, like, how quickly does that stuff affect you, and how long does it take to wear off, and all that kind of stuff? Well, this is different for every drug, right? And it's different for each person. If you take two different people of different size and health and percent fat and that kind of stuff, the drug is likely to affect one person in a different way that it affects the other person. So that's why you can't just give it, when you're giving someone painkiller, you can't just give the same amount to everyone, because it might be too much for a small 100-pound person and not enough for someone who's 250 pounds or something like that, right? So here's an example. The concentration C of a drug in the bloodstream T hours after it has been administered is approximated in milligrams per cubic centimeter by the following function. So notice they tell us T is greater than or equal to 0. Again, it goes back to that part, that number 5 that we just looked at. Ignore the parts of the problem that don't make sense. If you take this and you throw it into Desmos, let's do that. So let's do 7t divided by t cubed plus 18. Let's just make these x's. Here we go. So I've changed the t's to x's because it's Desmos and it likes to graph x's. But here's the graph we get. But this part over here doesn't make a lot of sense, right? This area where it's negative t, does that make sense? We're going to talk about the concentration of a drug in somebody's blood 10 minutes before they took it. That doesn't make sense, right? Before you take the drug, you shouldn't have any of it in your body. So this is just a mathematical anomaly that doesn't make sense for the problem we're working on. Now this part over here where it comes up and then it comes down and levels off, that looks a whole lot like what they have in here, doesn't it? Like this. You come up from the origin, it levels off, or it kind of peaks, and then levels off from there. If we played around with our Desmos, where's the right one? This one. Wait, where'd the other one go? Here we go. This one. It kind of looks like this curve. If we focus in on this positive part, that kind of looks like the curve in the book, right? That's the only part that makes sense. Starting at 0 and going forward from there is the part that's relevant. So basically, ignore all this because that's fantasy world. The drug concentration 10 minutes before you took the drug is 0, right? But you can go ahead and graph those in Desmos. Yeah, leave the page. Let's get rid of all these Desmoses. And then you're basically maximizing it, right? You're just using the first and or second derivative test. You have a little bit of leeway here as far as which test you actually use, but to figure out this exact spot where this maximum is. So that's really all the second half of chapter 3 is using the first and second derivative test that you learned in the first half of the chapter, but applying it to problems that are real world problems. So like, business problems, medical problems, stuff like that, right? Here we have one about sales where you're finding your profit, and then you just go through and work those. Here's one about folding boxes. This is kind of a traditional calculus problem. Here's one about chemistry. Here they're telling you t has to go between 0 and 20, so only look at those values on Desmos. Don't worry about things less than 0 or more than 20, right? So it's just basically word problems. So there's not a ton new in that section. Okay, 3.4. Actually, before we jump into 3.4, let's take roll. Oops, that's not what I want to do. I want to do this. I think I went one too big. There we go. Okay, let me take roll, and then we'll get into it. So let's see. And make sure I'm getting you if you're here, because remember, I'm going to do drops next week. So do we have Armin Kazarian? Okay, I got the 7 people in Zoom. Let's look at everyone here on YouTube. Okay, I might have a few people on this list that have already dropped, because I know a few people dropped this week. So it's probably that'll all get up to date next week. But so people I don't have: Jasmine A, Jennifer D, Isabella G, Cecil G, Dylan LB. I thought I saw him somewhere. No. Must be thinking of something else. Okay. And then Eduardo R, Juliana S. Everyone else I have. So if I just sort of called your name, make sure you make me aware that you are here. Okay? All right, good. We got that out of the way. Let's see. We got a chat here. The Scantron. So someone's asking me about the Scantron. Is it 825E? So it's in, they have them at least last week or whenever it was I went over there. They had them in the bookstore, in the VC bookstore. So you can just stop by there and get them. If you had bought them before, you'd have time to get one on Amazon, but there's probably not time for that now. But if you stop by the bookstore, you can get them. Be aware the bookstore's only open 10 to 2, and they are not open on Fridays. So I guess that means for this week they're open another 7 minutes. I don't know if you can get one from like an office supply store. I didn't check those, but yeah, that's the deal with the Scantrons. Okay, we got someone's here. Let's see. Okay, I got you, Alyssa. You're good. Okay. Okay, so 3.4, wait, is this the right one? Oh, yeah. Applications of the derivative in business economics. So I'm kind of going to work through the problems that are in the book here or talk you through them because reproducing them would take kind of a lot of work and probably be confusing. So I just want to show you how the problems in the book work, and then you can, if you question them later, you can go back and watch me talk about them, and then at least you'll have the written out version of these problems and help make sense of it. So there is going to be some introducing of some new definitions. We've talked about these a little bit, but they're now going to expand on the marginal analysis that we've talked about. We talked about marginal a little bit when we talked about derivative, but now there's an expansion of that. So in business and economics, the word marginal is equivalent to the phrase rate of change, or more precisely, the instantaneous rate of change. Usually in business, you can buy one more item, right? So you want to understand this is what they're saying is technically not exactly right from a mathematical standpoint, but for business, it generally holds up. So they're kind of taking this complex idea and they're simplifying it down to the setting where it usually holds for business. So technically, we use the derivative, which is the instantaneous rate of change. But when we talk about marginal revenue, we're using it in a very special case, which is to say, what if you buy one more item, right? Like if say you're a company, say you're Samsung, and you're manufacturing televisions, and the Best Buy down the street wants to buy 100 televisions of a certain brand, right? Well, they can buy 100 televisions or they can buy 101 televisions, but they can't buy 101.5 televisions, right? We're not going to cut a television down the middle and give them the left half. That doesn't make sense. So that's part of understanding what's going on when we use the word marginal, is that we're talking about one more. Now, that doesn't always exactly equate to the instantaneous rate of change or the derivative, because technically in calculus, 1 is a huge number. It's very, very large. When we talk about the limit as something goes to 0, 1 is monumentally massive, right? So there is a slight difference here, but you want to understand when we're talking about marginal revenue, cost, and profit, what we're talking about is those things and how it gets affected if you buy one more unit, or supply one more unit, depending on what side of the equation you're on, buying or selling, right? So just always think of it as the cost of one more unit or the revenue of one more unit. So marginal revenue is the approximate change in the revenue associated with a 1 unit change in the number of units sold. If the derivative of the revenue, it is the derivative of the revenue function. Revenue functions are commonly denoted with the letter R. The marginal revenue is commonly represented with MR. So marginal revenue. So whenever you see MR, MC, MP, and you're like, wait, what do those stand for? The M is for marginal. So marginal R, you go, okay, marginal revenue. Marginal CO, marginal cost. Okay, so you can kind of remember how those work. And the truth is, if you can remember one of these, you can remember all three, because the marginal revenue is the derivative of the revenue function. The marginal cost is the derivative of the cost function. The marginal profit is the derivative of the profit function. So if you just remember marginal means derivative, essentially, and that we use it to find the cost of producing one more unit, then then you're fine, right? So and the book, I don't usually see, in other books that I've looked at, they don't use MC, they just use this C prime, and you just remember that it's the marginal cost. But they kind of use both a little bit in the book. So for example, here we have example 1. The revenue realized by a company on the sale of X units of its product is given by the revenue function R of X is equal to X cubed plus 4X squared plus 160X. So that's the actual revenue. Okay, that is the revenue that is actually realized. So when they say realized, that means like it happened, right? You made that much money. Revenue is the money coming in. Cost is the money going out. Profit is the difference between those. So if they say the revenue realized by a company, they mean the revenue that actually is occurring under these conditions. So the revenue realized by a company on the sale of X units of its products. So they're saying that X is representing the number of units sold. I'm sure some of you are comfortable with that now and used to it. It's very common in this class where if you have a function, X oftentimes represents the number of units either produced or sold or whatever. So that means if we have 100 units, if we want to know the revenue when we sell 100 units, we can stick 100 into this function, simplify it, and that's our revenue. Okay. Now it says compute and interpret both R70 and R prime 70. So what is the revenue function evaluated at 70, and what is the derivative, the marginal cost, or the revenue, marginal revenue? So that's the thing. It's not just being able to calculate these, it's being able to interpret what they mean, right? So R of 70, you take 70 and you plug it into this function for R, right? So just everywhere there's an X, you're going to put a 70, you're going to simplify it, and the answer you're going to get is 373,800. That's what R of 70 means. It's 70 plugged into this R function. You get a revenue of 373,800. Now look at this sentence. See how descriptive this sentence is? That's the way you want to write things. Okay, I know right now, being raised on, texting and stuff like that, oftentimes people's messages have almost no information at all, right? But when you're in a business setting, you want to give lots of information, right? What you don't want is to be turning in reports and your boss is always like, these reports never have the information that I want, right? You want to give people information. You want to do it in a way where they don't have to read too much, but you definitely don't want them to have to come ask you about more stuff, right? So let's think about how well constructed this sentence is. This means that when the company sells 70 units of its product, it realizes a revenue of $373,800. See how concise and well written that sentence is? There's no more questions for us. It says when the company sells 70 units, it realizes a revenue of $373,800. We know exactly what we need to know. Oh, if we sell 70 units, here's what our revenue is, right? So this is where you want to get out of that habit, and I know it's hard because of the way the homework is, but you don't want to just answer things with a number, because the next person that comes along and just sees a number on a page, they're going to go, what does that mean? What is that supposed to represent? So if your recommendation, sometimes the company needs to know how many units to sell next month, and your recommendation may be, hey, we should sell 70 units next month because that's going to give us a revenue of $373,800. You put that in a sentence, and everyone knows what you're talking about. Everyone's on the same page, and they know where you're at. Oh, that's a good idea. Let's try to sell 70 units and realize that revenue of $373,800. Everyone's on the same page. Okay, so that's one reason these interpretations are so important, right? I know people get into math and they think like, oh, math's just about like getting some number at the end and then you put it in the box on the homework. That's not going to help you in the real world when you're actually trying to apply these things and run a business or get the high-paying position, on Wall Street or whatever it is that you're trying to do. Okay, you have to. The interpretations are very important. So for part B, what about R prime of 70? What does that represent? So we take the derivative, right? You obviously have to do that. If you're going to talk about marginal revenue, you need to find that marginal revenue, which is the derivative. So you take the derivative of this, x cubed becomes 3x squared, 4x squared becomes 8x, 160x becomes 160, right? So you can see how this is the derivative. So when we stick 70 in here, into this function, we get 15,420. Now, what exactly does that mean? Well, that's our marginal revenue. And remember up here we said the marginal revenue is the approximate change in the revenue associated with a 1 unit change in the number of units sold. So this means that if the company increases the number of units it sells by 1 from 70 to 71, its revenue will increase by approximately $15,420. So this is nice because this means you can always ask, maybe you're selling something big, right? Like buses or something where each bus is like a lot of money, right? So you might wonder, okay, what if our business, normally we sell 20 buses a month. What if we could find a way to sell 21 buses a month? What would our revenue be? So this is helpful because then you could see exactly, okay, well, if we sell one more bus per month, this is how much more our revenue would be. And then you can make a decision about whether or not that is a good idea for your business, okay? So this means that if the company increases the number of units it sells by 1 from 70 to 71, its revenue will increase by 15,420. Now, one mistake people make here is is they'll put in R prime of 71. So notice that it tells us in the interpretation, when we stick 70 into the revenue, the marginal revenue, that tells us the change from 70 to 71. If you were to stick 71 in here, that would tell us the change from 71 to 72. So be very careful. Like sometimes when the problem is worded differently, it may not be as obvious. Make sure you realize it's talking about selling the next product. So then you want to think of, oh, well, if I put in 70, that tells me the change from 70 to 71, right? So just be careful for that because I see some students make that mistake. And it's an easy mistake to make, right? So just kind of be careful with it. And then they say, oh, by the way, we could have used that other notation of MR, marginal revenue, but don't really need to. Right, so you've got this marginal stuff. I think you kind of get the sense of it. When you're having trouble on the homework, you just look at these examples in the book. I mean, they're pretty straightforward. You've got a cost. You've got marginal cost, and then you can compare the two. So you've got your function. You take its derivative. C of 600 is the actual cost to create 600 units. C prime of 600 is the cost of producing the next unit, right? So for instance, in this case, substituting 600 for x into C prime of x, we get C prime of 600 equals -2. This means that if the company increases the number of units it produces by 1 from 600 to 601, the cost to do so will decrease by approximately $2. Okay. So they follow a pattern here. These first ones are pretty straightforward. Yeah, so those are just basic like revenue cost type stuff. Let me move this over a little bit, see if I can make it a little, it's going to be too big, isn't it? Nope, perfect. Okay. So then we get into these ideas that are a little bit more complicated. They lay them out in the book, so if you need to look again, you can go back to the exact, you can rewatch this video, go back to the exact places in the book where they're talking about this and sort of work through it. But, business is kind of a complicated thing. There's lots of parts of a business that cost money, and sometimes you have to figure out the appropriate place to save money or spend money. Just like with, we talked before about cost, generally has two parts. The the fixed cost and the variable costs. So you can actually see that in most cost functions. You can go, oh, that's the term that's fixed, that's the term that's variable, and you can kind of see what's going on there. Well, there's another concept behind like how much should you order when your company orders something that it wants to buy, or if you're a store, how often should you be buying things in order to make it really efficient for you to make money. So for instance, usually with companies, the larger order that you make, a lot of times you get a better price on per item on the order, right? And a lot of times you get what's called an order price. So you like, okay, you're going to make an order, so right off the bat it's going to cost this much. And a lot of times that pays for like the person who's going to sit down and carry out the order, and they're going to fill out the paperwork and make sure everything happens on time. So there's some kind of like, sometimes there's just a fee for making an order. So those two things together might make you think, well, then shouldn't we always buy the maximum amount that we can, right? If I'm Best Buy and I sell our number one selling brand of TV is this one Samsung brand, should I just buy 1,000 of those TVs and we'll just store them in the stock room? And the answer is probably not. That's probably too many, right? But what are those considerations when you're deciding how much to buy, right? And this is one of the things that Amazon did right in the early days of Amazon, and it's one reason they were essentially able to put a lot of their competitors out of business, is because what they realized was, well, what if we have inventory is like how much of a product you have on hand. And so like one of the when Amazon first came out, they were just books, right? It was a bookstore, and then they just started selling everything. So we'll just keep the idea simple at the beginning and just say we're selling books, right? Well, when you go to the bookstore, you go to Barnes & Noble, or some of you probably aren't old enough to remember Borders. That was a big bookstore a while back. You could go there and they were just massive, massive bookstores, and they would have huge amounts of books. But there was always books they wouldn't have, right? Because there's a lot more books in the world than you can fit into any single bookstore, right? So one of the things Amazon did was realize that there's a lot of these books that aren't really worth stocking in a normal store, but people still want to buy them. So they said, what if we build some giant warehouses out in the middle of nowhere, right? Just in the middle of like desert Texas, or, you know, just parts of the Wyoming where there's just nothing, and you can buy land super cheap. They're near a freeway, so you can ship them easily, but we can build these massive warehouses, and we'll just ship the books to people. People don't have to come to the store. So what they did was they did that. They basically filled up these warehouses with every book imaginable, right? Every book out there. Even if there's only some book might only sell 5 copies a year, well, then Amazon might have 1 or 2 on hand in this warehouse out there. And so then what they would do is, well, that once or twice a year that someone orders that book, well, we've got it on hand, let's ship it to them. And that kind of is how they took off, was they could sell you any book because they have it, right? They've got it in there because they figured out, well, we can almost store things for free because we're doing out in the middle of Wyoming where land is, you know, not very expensive, because it's maybe not I'm not saying Wyoming's a bad state, but there are certain parts of Wyoming you probably wouldn't want to spend too much time in because they're just kind of desolate and deserty and hot, right? People don't go there a lot. Whereas if you tried to do the same thing, say you tried to have that same warehouse, that same strategy for Amazon, but you tried to do it in the middle of Los Angeles, you just couldn't afford to do it. It would cost so much money. That land and storing things would cost so much money that business wouldn't really work anymore, right? So you have to consider when you're buying things, there's actually a cost to storing things. So while it might make sense that why don't we just buy our whole inventory for the whole year? Why don't we just buy all the televisions we're going to need for the whole year? You might not have the space to store that many televisions, right? You might not have the room for it. And you don't want to buy too many because What if you buy 100 TVs of a certain model, and then all of a sudden the next day Samsung comes out with their updated version of that TV? And now people want the updated version, but you just bought 100 TVs that now people don't want as much. So now you're going to have to sell them at a discount. You're going to have to try to convince people to buy those old ones. Maybe don't have the kind of features that the new one has. Maybe a little bit smaller, slower processor in the TV, a little bit less RAM or whatever for when you're trying to use apps on there. So that's a little bit of what we're getting into, is this discussion about like, well, what's the right lot size to buy when you're trying to buy something? And we're going to look at the actual mathematics necessary to go through and calculate that. So I'm going to read this because they do a pretty good job summing this up, but I just wanted to kind of set the stage. So for retailers to do well, they must be careful about the number of units of a product they have in their inventory over some particular period of time. The business can control its inventory in either of two ways. One way is to place one order that will cover the entire anticipated demand. So in other words, you go, well, we're eventually going to need, maybe you put bikes together. We're eventually going to need 500 of these bike frames, so let's just buy them all right now. That's one approach. That's kind of one extreme of the spectrum. My allergies are not good. Sorry, that's why I keep choking when I'm trying to talk. Okay, so one way is to place one order that will cover the entire anticipated demand. This method is attractive since the company is likely to have enough units in stock to meet anticipated demand. It means you never run out, right? Sometimes you go to the store and they're out. The other day I went to get a burrito at Chipotle and they were out of like a type of meat. And then I went to the other Chipotle and they were out of like salsa. Or like, how do those places run out of stuff, right? If you're a place that orders like, you kind of serve one thing, you better make sure you have that thing, right? Otherwise, people are not going to be really happy about it. So you want to make sure that you have enough stuff on hand that you're not annoying your customers, right? That's not great. So you want it is likely you'll have enough units in stock to meet anticipated demand. The company will incur only one ordering cost. So a lot of times there's a cost for each. There's like a flat rate for each time you make a purchase. Like I say, to cover the paperwork and the person who has to run the paperwork and organize it and stuff. The least number of times you have to order, the least times you incur that fee, right? The company will incur only one ordering cost, but it may also incur carrying costs, such as storage and insurance costs, as well as costs due to the possibility of obsolescence, spoilage, or breakage. Carrying costs are sometimes called holding costs. Okay, so there's a bunch of new terms in there. So if you're going to order a whole bunch of stuff at once, because you know your company needs it and you just want to order it, well, you have to store it somewhere. And that costs money, right? You might think, well, how does it cost money to just put it on the shelf? Well, it costs money to run that storage facility where you're storing things. So the people working at the storage facility itself, they mention insurance. You want to have those things insured. What if a tornado hits your storage facility? You're just gonna eat the cost of all those product, or do you want to have insurance on it? Well, that costs money, and obviously, the more items you're insuring, the higher the insurance is going to be, right? The possibility of obsolescence, like I said, you're a store, you buy 100 Samsung TVs, and the next day they come out and announce the next version of that very same TV. That's probably not a good feeling, right? Spoilage or breakage. So spoilage is usually more for food products that don't make it to where where they need to get in time. Or breakage, things just break, right? If you've ever worked in any of these kind of industries, like things happen. Units fall over when they're getting unloaded off the truck. Something hits the truck and this, part of the stuff inside gets ruined. All sorts of things can happen. So carrying costs are sometimes called holding costs. Okay. Another way is to place a series of smaller orders throughout the time period. This method is attractive since it keeps carrying costs down. So it reduces all those costs we just talked about. So you can see there's a balance here, right? There's like a back and forth shift of, well, I could buy everything at once, and that would make some costs go down and some costs go up, or I could have a bunch of smaller orders, and that would make some costs go down and other costs go up. So it's hard to know, well, what's that sweet spot where I can make the right number of orders and it's the most efficient use of our money, right? So the total inventory cost is the sum of the carrying costs and the reorder costs. So the problem for a business then is to determine the lot size. That is the number of units in an order that will minimize its total inventory cost. This is the minimization problem for which you can use the optimization techniques of 3.3. So basically you're using first and second derivative test in order to figure out what your lot size should be. If I'm a television store and I'm ordering TVs, should I order them 5 at a time? Should I order them 10 at a time, 30 at a time, 100 at a time? I don't know. That's what I have to determine. I have to determine my lot size, right? So we will analyze this problem by making 3 assumptions. The sales of the product are made at relatively uniform rate over the time period under consideration. So we're not talking about like Black Friday where all of a sudden the shelves are empty. We're just talking about like sales of the product are made kind of continuously, right? That the lot size X for each reorder is the same. So we're not varying lot size. We're not saying sometimes you should order 3 TVs and then the next time you should order 12 and then you should order 30 and then you should order 7. We're going to pick a number X and we're just going to go with that, right? Sometimes that's how you would do it in real life. Sometimes this is just a way to simplify the problem down so it's a little bit easier to work with. And our third assumption was what? I'm trying to remember. That as each inventory of the stock falls to 0, another order immediately arrives. Okay, so that may or may not work in the real world. Just like, the other day when I was trying to get a burrito and all of a sudden they didn't have the stuff that I wanted, right? They thought something was going to show up, but it didn't come in time. You never want to sort of be in that position, right? I remember one time I was trying to get food at Jack in the Box. They ran out of ketchup. Didn't have ketchup in the store. If you're a fast food place that serves burgers and fries and stuff, it's probably important that you have ketchup, right? So that's one thing. You want to make sure that you're getting those orders in there in a way where that you're going to get the next order before you run out, or like in this case we're simplifying it as you run out, but that's like a real world consideration. Because when people come to their business and you do one thing and you're like, sorry, we ran out of the one thing, then that means you're not doing business, right? So that's our third assumption. As soon as the stock falls to 0, the other order immediately arrives. Now, that's what gives us this weird picture here. You might look at this and go, what is going on there? Well, what's going on is we get a shipment, so we have X items. Whatever we're going to figure out, X, we're going to decide what X is. X is our lot size, right? So C of X is the total inventory cost for lot size X. H of X is the carrying cost for lot size X. R of X is the reordering cost for lot size X. Okay? So we can see what's happening here. Every time we get a shipment, we have X items because that's our lot size. And then we said that we're uniformly selling these. So it's not like we have one day there's a rush and then one day we don't sell any. They're just gradually going down to 0. And once we hit 0, a new shipment arrives. And then we're selling the products and they leave, and then a new shipment arrives. And we're selling the products and they go. Once we hit 0, a new shipment arrives. So that's what this weird looking graph is, that I know sometimes is a little tricky for people to interpret. It just means we get a shipment, we've got X items. When we get down to 0, the next shipment arrives. Okay, that's sort of idealized. You hope that's the way that it works in the real world. If you're running a business, that would be perfect. As soon as you sell that last item, boom, the truck shows up with more items. Right? That would be awesome. Since both carrying cost and reorder cost depend on the lot size X, they are functions of X. Therefore, the total inventory cost is a function of X. In symbols, we have that C of X is equal to H of X plus R of X. So basically, the total inventory cost is equal to the carrying inventory cost plus the reordering cost. Our goal is to minimize that, right? We want to minimize that. So, At any given time, the largest inventory in stock is X. You can see that from our graph. It starts, we get a shipment of X items because that's what the lot size is, and then slowly we sell those items till it gets to 0, and then we get another shipment, and it does this, okay? So since the units sell at a uniform rate, we can calculate the average inventory during the time period, and that's going to be excuse me, that's going to be X divided by 2. Why is that? Well, we're selling them at a this is one of the reasons we make this simplification. Since they're selling at the same rate, when we get a shipment, we have X items. When they're all sold, we have 0. So what's the average of X and 0? Well, it would be X plus 0 divided by 2, right? That's how you find the average. You add the two numbers together and then you divide by 2 if you're finding the average of two items. So X plus 0, when we have the most, is X. When we have the fewest is 0. X plus 0 is X. Divided by 2 is X divided by 2. So this isn't just some magic number. That's just the average. It's the average number that you have on hand at any given time is X divided by 2. So they just use that to simplify things a little bit. Now this is going to look kind of intimidating, but it's not too bad actually. So the carrying cost is the holding cost per unit times the average number of units. Because if you think about it, like we're up here, our carrying cost is like kind of high because we have lots of units, right? And down here, the carrying cost is low because we have fewer units. But in reality, the insurance company doesn't care how many units you have every single day. They're like, just tell us the average number of units that you have, like at any given time. So they know sometimes there's going to be more if a shipment just came in. Sometimes it's going to be less, but they want to know what's the average overall, right? They don't want to know, well, on Monday we'll charge you more for insurance because you have more units. On Friday we'll charge you less. They just want to know what's the average so we can make this simple, right? So you've got your holding cost per unit times the average number of units, which is X over 2. So the holding cost per unit is H of X is the holding cost per unit times X divided by 2, the average. So that's where this looks like it's kind of a fancy thing. It's not. They're just finding the average cost. They're averaging the cost over the course of a month or whatever our unit time is. The reordering costs are the cost that it's going to cost you per order times the number of units sold during the time period divided by the lot size. So that's just going to be X is our lot size, remember? So our C of X is H of X plus R of X. So that's where they're breaking it down. It looks fancy, but there's not too much stuff going on there. Let's see if I can make this a little bigger, easier to see. Okay, so let's kind of talk our way through this problem. A company anticipates selling 3,200 units of its product at a uniform rate over the next year. So uniform, again, just means like steady rate. We're not having up and down days. It's just over the course of a year, every day we sell about the same number of these things. Each time the company places an order for X units, it is charged a flat fee of $50. So every time I call up and say, hey, we want to make another order, they say, okay, well, it's $50 right off the gate. And then the carrying costs are $32 per unit per year. That's how much it's going to cost you to hold on to that stuff. So we want to minimize the number of times that we order because we don't want to pay that $50 flat fee. But we also want to minimize the amount of money that we have to pay for each unit that's sitting in storage, which is $32 per year. Okay, so we have these two opposing things. One is telling us to make lots of orders. One is telling us to make hardly any orders. So we have to balance that out. How many times should the company reorder each year, and what should the lot size of each order be to maximize inventory cost? And what is the minimum inventory cost? Okay, so since the company anticipates selling 3,200 units, it can place anywhere from 1 to 3,220, right? So those are the extremes. We could order one item at a time every time we need one, and we would have to do that 3,200 times. I mean, that's a little silly. Depending on what we're selling, that's probably a little silly because, again, as soon as you sell one, you better make sure that next one shows up immediately, which is one of the assumptions of our problem. But in real life, that wouldn't work, right? If you sell cars at a car lot, and every time you sell a Corolla, well, by the time the next Corolla gets delivered, you may have lost 3 or 4 sales because you didn't have any Corollas on hand, right? It's just so, it depends what it is that you're selling. The maximum is 3,220 units because that's the number that you expect to sell in a year. So you don't want to buy 5,000 units if you know you're only going to sell 3,200. What would the point of that be, right? So we need to find the number of orders that will minimize inventory costs. So to do so, we need an inventory cost function that is valid on the interval 1 to 3,200. Why is that? Because that's the number that we can have in inventory, right? We can be ordering one at a time, or we can order 3,200 at a time and just do the one order. So that's really the only interval we care about. We don't care about negative numbers. We're not going to make orders of negative 70 units. That doesn't make any sense, and it doesn't make sense to go bigger than 3,200. 0 doesn't make sense either because you're not going to call someone and say, hey, can we put in an order for 0 units? 1 is the smallest number that makes sense, right? So we know that the general form of the inventory is C of X is equal to H of X plus R of X. That's what we did on the previous page, where H of X is the carrying cost per unit times X divided by 2. That was all that work we did up here. They're just sort of summarizing what we talked to right above it. So in this case, we actually plug these in. So we've got the carrying cost per unit. They gave us in the problem is $32. So see how it says $32, the carrying costs? So then $30 shows up right here in the carrying cost per unit. So H of X is 32 times X over 2, right? Because they gave us this amount as 32 in the problem. Now that simplifies to 16 over X because 13 divided by 2 is 16, so 16X. Okay, so H of X, not too bad to calculate. What about R of X over here? Let's see. So R of X is our cost per order times the number of units sold during that time period over X. So they gave us in here that was a flat fee of $50. That's our cost per order is $50 given in the problem. So that's why this became a 50. The total number of units we're selling in the time period, we're talking about 1 year, and we expect to sell 3,200. They told us that right at the very beginning. The company anticipates selling 3,200 units of its product at a uniform rate over the next year. Okay, so 3,200 for the time period. And then X, that's just X. That's the number we're actually selling. So 50 times 3,200 is 160,000 divided by X. Okay, so we've got that. So remember that C of X is H of X plus R of X. So we just figured out H of X over here, and we just figured out R of X over here. So C of X is the sum of those. So then we add those together. See, the 16X is coming from here, and the 160,000 divided by X is coming from over here. And they're saying, by the way, this function only makes sense between 1 and 3,200 because, again, we're not going to have that's our lot size, right? X is our lot size. We don't want a lot size of X than 1, of X less than 1. That never makes sense. And why would we want to buy more units than we're going to sell in a year? That doesn't make sense either, right? So we've got our C of X function. And if we're going to be using the first and second derivative tests, we probably want to figure out the first and second derivatives. So that's what we do here, right? You take the first derivative, you can see this is the derivative of this, right? 16x becomes 16. This is 160,000 over x to the negative 1. So when you use the power rule, you end up with a negative and down in front, and then you get an x to the negative 2, therefore x squared in the bottom, right? So this is just the derivative of this thing. Hopefully you're all nodding your head going, yeah, I get it. Okay, if not, feel free to ask a question. But the derivative part hopefully is straightforward for you. Then we take the second derivative the same way. The 16, when you take the derivative, just goes away, right, because it's a constant. And then this would really be negative 160,000 x to the negative 2. When you take the derivative, the negatives cancel, and you get x to the negative 3 on x to the negative 3, which means we get x to the third on bottom. Okay, so we have the first and second derivative test. You have some choices. There's a little bit of, there's a little bit of overlap in ways that you can use the first derivative and second derivative tests. It just depends on each individual problem. So feel free to use them how you like. Here we're looking for, we want to minimize c of x by computing the derivative and determining the values of x for which it is 0 or undefined. We're looking for the critical values for our function here, right? So we take the function that is the first derivative, set it equal to 0. So what did they do here? They multiplied the entire equation by x squared to get this polynomial here. Factor out the 16. Factor this difference of squares. And you get x equals negative 100 or positive 100. Well, negative 100 already doesn't make sense, right? We're not gonna place orders of negative 100 units. What does that mean? We're actually returning units to the company. It doesn't make any sense, right? So the only value that makes sense is positive 100, right? So let's take a look at this graph. I think did I delete it? I had it open. I had this one open a little while ago, but I probably deleted it with all the at one point having too many Desmos graphs open. So let's see. Oops, that's not right. Now, one thing that's a little helpful here, notice that when I put this into Desmos, I don't see any graph. So one thing you can do is just sort of scroll out, but even then, like, I'm not seeing any graph here. Where's that graph that we're looking at? You go a long ways before you even see that. Oh, there it is. We finally found it, right? So that's kind of a pain. So what you can do, remember in the problem they told us that this function is only valid when x goes between 1 and 3,200. So why don't we make that our x range for the graph? In other words, I'm going to go in here, hit the wrench, and see where it says x-axis. It's always nice to leave a little bit of some negative just so you can see where that axis is. But on this side, I'm going to go 3,200. And sometimes it's nice to leave a little buffer on the end, but whatever. And we can see, so at least we know the x range, and then you can mess with the y range just until you see your graph. Okay, looks like we got it. Well, let's go one more. Okay, so here's our x range. Here's our curve. It looks like remember, what are we trying to do? We're trying to minimize this thing, right? Well, it looks like the minimum happens down in here somewhere. So that means we can now kind of focus in on this range. See this negative part that doesn't make sense? We can totally ignore all this negative value because we're not going to buy lot sizes that are negative. It doesn't make sense. So we want to zoom in on this part where that minimum is occurring and try to see about that. So let's now change our x value. Looks like maybe let's see, what are these, 200? Why don't we try going from 0? Well, let's make it like negative 10 to say 250. And we have way too much y value. Let's get rid of some of this. We don't really need any negative y, so why don't we just make it like negative 7 to say... Oops, no, negative 7 to like... Well, that helps us see. We've zoomed in on that area now, and we can kind of see this is our curve. And look where that minimum's happening. Looks like it's happening at 100. Oh, you can't see it on the graph. Let me do this. There we go. That minimum's happening, it looks like, at 100. And what did we see when we were working on the problem? That was one of our critical values, was 100. So that's good news. Look, oh, it looks like we know what we're doing. So we can just double check, and you can use this using either the first or second derivative test, right? We could see that if we make a sign chart using the first derivative test, we're decreasing here, and then we're increasing over here. Well, if you're decreasing going into increasing, that sure seems like a minimum. So it sure seems like we've proved mathematically that's a minimum. Also, you can use the second derivative test and show that over this whole region, you're concave up. Well, if that's your critical value and you're concave up, then that must be your minimum, right? So see how a lot of times the first and second derivative test, you can use either one of them in order to justify what you're doing. Not always, but a lot of times you can switch back and forth to justify that that's the minimum that you're looking for. So then they justify. Therefore, to minimize the inventory cost, the company should place 3,200 divided by 100 equal to 32 orders of a lot size 100. So basically, we want our lot size to be 100. That's the X that we've solved for. That means we're going to have to do this 32 times. But mathematically, it looks like that's how we minimize those costs. We're going to make 32 orders of 100. And of course, we have to double check our business and go, can we order 100 at a time? Does that make sense? Are we risking obsolescence where we end up with a bunch of old TVs if we do that? Like, you know, you want to double check the reality and make sure that that makes sense. But in an abstract mathematical sense, that's the right choice. Lot size of 100, 32 orders. Okay, and you can see their picture looks kind of like ours where we had that curve and they pinpointed that minimum right there at 100. Okay. Any questions on that? Are we good? Like I say, it's I'm explaining. If you just tried to read this on your own, you might struggle. But with this explanation, I think it'll make sense where a person can kind of walk through these. Right. Okay. Let's go to, okay, elasticity is the thing I want to make sure that we don't run out of time because this is a big one. A lot of these terms you're going to hear when you're taking your economics classes and, you know, your different classes that you look at. Elasticity is one that comes up. So elasticity is this idea. We'll get to the formal definitions in a minute, but I kind of want to give you an idea firsthand. Basically, there are certain things that affect the cost of other things. Okay, so for instance, this happened last winter, right? With the issues that are going on over in Ukraine, it affected gas in that part of the world. Gas being moved around. Well, all of a sudden, that affected supply of gas that a lot of people in Europe use for heat in the winter. So you saw gas prices, some outrageous gas prices that people were paying. Their cost of heating their places was just skyrocketed because all of a sudden there was no oil available, to process into different forms in order to burn as energy to heat the house that they were living in. So a change in one item and its supply or demand can affect other items as well, and their cost and their supply and demand and all sorts of things. So elasticity is basically looking at the change between two variables. How much does the change in this one variable affect the change in the other variable that you want to look at, right? So one popular question to answer this is, can we raise the price of the item that we're selling, right? What if you could raise, maybe you sell something that's $5 and you realize, if we instead charge $6, we would sell almost as many units, but we would be getting $1 more per item. Well, that might be a good idea then, if you could do that. But what if changing the price from $5 to $6 meant no one was going to buy it anymore? right? You are hardly going to sell any. Then that's probably not a good idea, because the few, maybe it's a burger at Carl's Jr. or something. Maybe they're charging $5 for a burger and they're selling lots of it. And they go, I think if we charge $6 for this burger, I bet you sell almost as many. And maybe they do. So they raise the price and they actually end up making more money, because they might sell a few less burgers, but they're making another $1 on every single burger that they sell. So in that case, it is profitable to do so. But what if sometimes, they talk about what the market will bear. Sometimes raising the price to $1, people just aren't going to tolerate it. There are certain things people just won't pay for, right? Like, look at apps. People will spend all this time on apps that are kind of a pain to use. But if there's one nice version of the app that costs $1, a lot of people just won't do it. I'm not paying $1 for an app. They'll go spend $7 for a Starbucks coffee, but not paying $1 for an app that I'm going to use multiple hours a day, right? It's just there are certain things that people just won't pay for. So then you want to know, okay, well, what if we have this app and it's free, or maybe it's $1, but maybe we charge $2 for it, and people are just nope, $2, that's ridiculous. I'm not paying $2 for this thing. And then your sales plummet to almost none, right? You don't want that. So that's what this elasticity is all about. When a change in one variable causes a response in another variable, elasticity is the measure of the size of the response. In other words, when we change the price of our product, do we get a big change in sales, or do we get a small change in sales, right? You can think of it that way. Elasticity measures how sensitive the value of one variable is to the value of another. If a percent change in the input variable causes a relatively large change in the output variable, the relationship between the variables is called elastic. Right? If a percent change in the input variable causes a relatively small change in the output variable, the relationship between the variables is called inelastic. So what you'd like to be able to do is increase the price of your product, but not have that really affect the number of sales that you sell, right? You would like that to be inelastic. Say, I want to charge an extra $1 for every item we sell, but I don't want it to affect or at least I want it to affect in a very small way the number of sales that we make. If you go to sell that product and you say, I'm going to charge $1 more, and all of a sudden your sales plummet, then you had an elastic situation. So that's what that word means in this sense, okay? So I know it's kind of dry when you just read this. You're like, what are they talking about? But just think about it in terms of when you're selling a product and you want to change the price, is it going to cause a big change or a small change in the number of products that you sell? Okay. Yeah, so they're just kind of summing it up here. When the variables that are related are demand for the commodity and the price of the commodity, we speak of the elasticity of demand. Okay. Elasticity of demand is denoted with the lowercase Greek letter eta. I think that's how you say it, is eta. This is actually not one of the Greek letters we use too much in math. And is computed by dividing the percent change in the quantity demanded by the percent change in the price. So that just let's stop and think about what that means for a second. Elasticity of demand is denoted by dividing the percent change in the quantity demanded by the percent change in the price. Okay, so we're looking at those 2% changes, and if they're relatively close to each other, then that fraction will be 1, right? It'll be 1 if you make a 5% change in price and that causes a 5% change in demand, then those values are relatively close to each other, right? And in mathematics, this little triangle, that's actually a Greek letter delta. So delta usually in mathematics or science means change. So what is the change in this thing, right? And the percent change in P is represented by delta P over P. That makes sense. So we have two things. We have delta Q over Q and delta P over P. So if you sell something for $1 and you change the price by a dime, then you've just changed your price by 10%, right? But if your item is $100 and you change the price by 10 cents, then you just changed it by a very small amount, right? So that's what delta P over P is telling you. How much is your change in price relative to the actual price? Because a 10 cent change in price would be a lot for something that costs 10 cents, but it would be nothing for something that costs $10,000, right? So we want that percent change there. Now, since eta is computed by dividing the percent change in quantity demanded by the percent change in price, so now I know it looks like it's kind of fancy, but it's just putting these two ideas together. We've got the percent change in Q, so our demand, divided by the percent change in our price, and we end up with we'll sort of skip a lot of the breaking this down, but you can see there's a limit as the change in price goes to 0, so we're using a limit there. This letter is epsilon. It's not really important, but they point it out here just so you know what to call it when you see the symbol. We've got epsilon is equal to limit as the change in price goes to 0 of eta, and then we follow some work, and they give you the formula for that right here. So if you're interested in exactly where that formula came about, you can just kind of follow those steps, but I got you sort of started with understanding the basics. Right. So point elasticity of demand. The point elasticity of demand, epsilon, is defined mathematically as epsilon equals negative P over Q times dQ dP. Remember, that's the change in Q with respect to P. That's your derivative right there, dQ dP, where Q is the original quantity demanded when the original price per unit is P. So P and Q are your original quantity and price. Point elasticity measures the elasticity at a particular point and is interpreted as the percent change in the demand for a 1% change in price. So, if you make a 1% change in price and that gives you a 1% change in demand, then those values are pretty close together. If you make a 1% change in price and that gives you a 10% change in price, then that could be a lot, right? That might be more than you want to do. So you're going to have the problems where basically they give it to you. You're going to calculate this derivative, right? They're giving you Q, where P is in dollars, and you're going to calculate that derivative in order to go through and figure it out, right? So you can see right here, they take the this is the part where they take the derivative. Like here, they're setting it up. Excuse me. Then they take the derivative. You get down to the bottom, and then you've got your interpretation. So if we have an epsilon equal to 0.67, how do we interpret that? Because that again, these calculations make no sense if you don't understand, well, what does it mean? What does the interpretation mean? So for that problem, if the price of each unit of this product is raised by 1% from $27 to $27.27, the demand for the product will decrease by approximately 0.67 from 500 units to approximately 497 units. That's a pretty small decrease, right? You're only selling 3 less units, but you've raised the price 1%. Might be a good idea. According to the definition of elasticity we gave previously, this would constitute an inelastic relationship between price and demand. So we were able to raise the price 1%, and the number of units that we don't sell now is less than 1%. So we're in this case, it sort of is indicating to us that we're ahead, right? This might be this might be a smart decision to make. Not going to make a huge amount of difference, but it might be a good idea, right? Because you can always just, don't memorize this, just think about how it works. If you're going to the store to buy something and it turns out that since the last time, say you're going to Costco, you're going to buy a TV, right? And you're like, great, I looked at this TV, I did my research, I compared costs, I'm going to go buy that one at Costco. And you get there, and since the last time you were there, they raised the price of the TV by $100. You might still buy it, but you might not, right? You might go, oh man, $100, I don't know if I want to buy this thing anymore. And some people won't. So you can watch this relationship. As the price goes up, demand naturally goes down. Okay? Some people will still buy the TV when it's $100 more, but some people will go, that's just $100 I don't have, and they're not going to buy the television anymore, right? The other way, think about it. What if you think the price is a certain thing, you're on your way to Costco, you show up to buy the TV, and it's $100 less than it was previously listed. It's now cheaper than you thought it was going to be. Are you going to leave without buying it? Probably not. Most people don't go, what? You're charging me less than I thought? I'm out of here. They're like, oh, great. That's $100 I get to save, right? So you can always keep these ideas straight by just remembering, how does price affect demand? As price goes up, it's going to drive demand down. As something gets more expensive, fewer people can buy it. And as price drops, more people can buy it, so demand will naturally go up for most things, right? So if you can keep that straight, you usually can keep straight these ideas that we're talking about here. So then they go through and do the elasticity for revenue. The same idea. They go through, they sort of construct everything, and then they just give you the formula at the end in here, right? So let's look at this. This is how you're going to interpret these. So elastic, unit elastic, and inelastic. This is on page 285 of the book if you're looking. So if epsilon is greater than 1, then r prime of p is less than 0, means that the total revenue falls with price increases and rises with price decreases. Demand is elastic. Okay. If epsilon is equal to 1, then r prime of p equals 0, means that the total revenue is unaffected by changes in price. Demand is unit elastic. In other words, if you make a 5% change in price, it's going to make a 5% change in demand, or in this case, revenue, right? So in other words, they're just going to match each other. If epsilon is between 0 and 1, then r prime of p greater than 0 means that the total revenue rises with price increases and falls with price decreases. Demand is inelastic. So that's kind of what you want. You're hoping you want revenue to rise with a price increase, and you want revenue to fall with a price decrease. You want to be able to increase your price and have that increase your revenue, right? You don't want to increase your price and all of a sudden your revenue drops. That would not be the right direction. That would be bad, right? Right. Okay. So I know some of those formulas are kind of complicated, but just keep in mind you've got the book here and you can work through them. You can look at that stuff. Try to look at the parts of the book that I walked you through. Try to look at them a little bit and see if you can make sense of them. If you need to watch the video again, go ahead. See if you can make sense of the part that we're talking about so that you understand those concepts. 3.4 is really difficult if you don't understand those basic fundamentals of business, which is, like we talked about, the one that's easiest to keep track of. As price goes up, it's going to drive demand down. As price goes down, demand will go up. More people are going to buy a product that's cheaper than when it's expensive, right? So you just want to keep track of all those things, from the marginal cost and profit down to the inelasticity and all that kind of stuff. Okay, so for this week, make sure you take your test. Don't forget to do that. That would be really bad. So those of you who haven't taken the exam yet, make sure you get that taken care of. Make sure you're getting caught up on the homework if you've gotten behind, because like I say, at the beginning of next week, I got to go through and sort of see people that aren't realistically going to be able to catch up, and I got to cut them loose. So please catch up on the homework if you are trying to do so, if you're trying to stay in the class and complete it. Take care of that this weekend. And then just stay on top of the homework. We'll roll stuff out. We'll talk about, I didn't get to chapter 4 today. I thought I might, but we didn't. So I will talk about that on Tuesday, and then we will go from there. Okay? So, as always, I will close down the YouTube stream. Anyone who wants to talk to me, come jump over into Zoom. Just use the Zoom link on Canvas. Come talk to me, and I'll answer whatever questions you want. Whatever you want to talk about, let's talk about it in Zoom. Okay, thanks, everybody. I'll see you next week.